In my opinion, the biggest challenge for students when they first meet vectors is understanding how they differ from scalars and coordinates. Even for quite bright students, it takes some time for them to appreciate the subtleties that exist between a coordinate, which is simply a point in space, a position vector, which is a route from the origin to a point in space, and so a position vector is fixed in space, and a standard vector, which is a route with a direction and a length, and in a sense it floats in free space. Now, most important of all, teachers need to emphasize that vectors have a size, which is often called the magnitude of the vector, and a direction as well. Now, when students first meet vectors, it will probably be in the context of abstract geometric proof. As a result of this, it's natural for teachers to use many visual tools to help learners develop a rich mental picture of the way vectors can be manipulated. A great way to introduce vectors is using the standard arrow as a visual representation of a vector. This can be done on smart boards quite nicely, where you can move the arrow around, or simply with paper arrows, which they can stick on the board with blue tack and move around. You can then invite them up obviously to the board so you can move them around, understanding that they float in space but without changing direction. Then, when attempting the kinds of visual proofs they're asked to complete at GCSE, they can notice that there are several ways around the shape, all of which lead to the answer, because it is a very important aspect of it that you can do it in several different ways when you're doing a geometric proof with vectors. Handling the vector algebra is actually quite straightforward, although students will naturally make the mistakes they normally make when manipulating algebra, which is collecting like terms and making sign errors when expanding brackets. Now, the last thing I want to say, and this can't be overstated, is that students must be able to visualize the vectors, or they're going to have real trouble proving that two vectors are parallel or that 3 points are collinear. Now, these are topics which will all be covered in the Shape and Space 2 module. Students are expected to apply vectors in the abstract setting of geometric proof, but as you quite rightly point out, soon they'll be asked to apply them in kinematics questions also. This opens up quite a different set of misconceptions from the type encountered in abstract geometric reasoning. The biggest misunderstanding is without doubt regarding the signs of the values that they need to plug into the Suvat equations. This tends to occur because the student has ignored the wise advice from their teacher to construct a good diagram that clearly states which direction is positive. Only once you have decided which way is the positive direction can you assign sign values, positives and negatives, to the displacement, velocity and acceleration of the particle. This is best shown by an example. Let's take the case of a ball. It is projected into the air from a height of 60 meters above the ground and with an initial speed of 20 meters per second up into the air. A student could be asked to find when it hits the ground. Now, let's just talk about some of the misconceptions here. It is very difficult for students to accept that the object is moving in one direction but accelerating in the opposite direction at the same time. The key thing to remember with projectile motion, if you're throwing an object straight up into the air, is that the object is always accelerating towards the ground, even when it's rising up in the air to its apex. Hence, if upwards is taken as positive, acceleration will always be roughly minus 10 meters per second squared. So acceleration does not give the direction of motion. Acceleration is in fact velocity, which gives the direction of motion, and this velocity changes from positive to negative as the object rises and falls. Naturally, velocity will also take the value of 0 when the object, the ball, is at its apex, its greatest height. Now, students also have a tough time accepting that displacement isn't the same thing as distance travelled, and so can be negative also. In our example, we need to find when the object hits the floor when it's impelled from a height of 60 meters above the ground. So S is going to be negative 60 in our example, because it's going to go all the way up, all the way back down to when it's at the height which it was thrown at, and then a further 60 meters down to reach the floor. The origin, you see, is always taken to be wherever the object began its journey, its position, when u was 20 meters per second, And now we can finally solve our Suvat equation successfully, provided we pick the right formula, which, to be honest with you, most students will agree is the easy bit. So, have a quick look at the four formulas, and I hope you will see that S is going to be ut plus a half at squared. That's the formula we need because we have S, U, and A, and we're looking to find t, the time at which it hits the ground. All that's left to do when you plug those values in is solve a quadratic equation. Now, I've tried to make this quadratic equation quite a nice one to solve, so please, by all means, pause the video and give it a try, but you should find, after you've tried, that t equals 6 seconds. If you want to understand kinematics, you must demonstrate with examples. Even just throwing a pen up in the air can sometimes get your point across, but nowadays we have a range of fantastic dynamic resources that demonstrate the three variables within Suvat changing. Computer simulations of kinematics are available from many sources, but if you're really ambitious, you can get the stop clocks out and confirm the theory with the practice. I've observed lessons before, actually, where students are asked to drop objects from a third floor window in order to estimate the height of the building by timing the descent. This engages the learner by helping them to see that the theory works and can be incredibly useful. So if you're ambitious and adventurous, why not give that a go? My own personal preference utilizes the Moving Man applet from Colorado University. It's a great dynamic display of constant acceleration that helps students appreciate how the three variables interact and influence each other within Suvat. Take a moment, if you like, to open up this applet and play around with it on your own computer. Make sure you tick the boxes for showing the velocity and acceleration arrows so you can get an idea how these change as the man moves up and down the scale. It's the velocity arrow which changes direction, whereas the acceleration arrow is always pointing in the same direction. Now, there are many other great resources out there, so please see what you can find. But these applets really are very, very useful if you want to show a class how the acceleration always stays constant, but the velocity vector is the one which changes. Poor mathematical literacy can hold back students in all applied areas of mathematics. In many ways, the problem is not just a narrow mathematical vocabulary, but the difficulty that students have in reading the text carefully and paying attention to all the details. Encouraging students to underline or highlight relevant points can go some way towards addressing these issues, but there's no doubt that most students, 90% of students, will tell you that they find wordy questions the toughest to answer. To be honest with you, I feel the same way as well. If I have a wordy question, I have to sit there, think about it, and extract the relevant information very carefully. Now, English as an additional language students are particularly prone to finding these problems tricky for obvious reasons, but it's not just EAL students who find it tricky to read a block of text and turn it into mathematics. Like I say, I think we all do to some extent. It's far easier if you're just asked to factorize or solve or expand something because you know there's a rule to do that. But if you've got to read and interpret, that's a whole separate skill on its own. It involves comprehension. Okay, generally speaking, the ability to convert a paragraph of information into the relevant equations comes with mathematical maturity, or in other words, practice. It is also more important now than ever, as the new syllabus will include more questions that require mathematical applications to real-world problems. Apparently, there are to be fewer questions that simply read, solve, factorize, or expand, but more questions that describe a situation where students will eventually need to apply these techniques after constructing the correct mathematical equations from a given context. Now, kinematics can, of course, cause lots of problems for students with poor mathematical literacy. The biggest problem tends to be students recognizing the distinction between velocity and acceleration. As I mentioned earlier, it's vital for students to recognize this distinction. They'll often become confused, for example, if you describe a situation, say, where a car that is decelerating overtakes another car that's travelling at constant velocity or even accelerating. They don't believe that is possible. Now, clearly it is possible if the car which is decelerating is actually travelling at a much greater velocity than the car which is travelling at constant velocity or indeed accelerating. So that situation can happen, but they find it very hard to visualize. That's why it's so useful showing them the Java applets or showing them perhaps practical demonstrations. It makes no sense to them as they mistakenly treat velocity and acceleration as the same thing, almost interchangeable within their own head. You must make it clear that acceleration is not the same thing as velocity. It is, in fact, the rate of change of velocity. Now, this brings us to another problem which is related to this, and that is the meaning of the words rate of change. Sometimes a question will actually introduce acceleration as the rate of change of velocity. So they will not use the word velocity, they will simply say the rate of change of velocity, and they obviously mean the acceleration. Now, it's crucial that students are aware of the fact that velocity is the rate of change of displacement, and acceleration the rate of change of velocity. This is easily demonstrated actually if students have already studied rates of change in calculus. If you take s equals ut plus a half at squared, then differentiate it once, what you've found is the rate of change of displacement with respect to time. And that should be, of course, velocity. Well, sure enough, if you differentiate s equals ut plus a half at squared with respect to t, you will find that you get v equals u plus at. So you obtain one of the other Suvat equations simply by differentiating. And when you differentiate, you do in fact find a rate of change if you're differentiating with respect to time. Now, if you do it once again, you'll simply get dv by dt equals a, and that shows you that velocity differentiated is in fact acceleration, which is lovely because obviously velocity is the change, acceleration is the rate of change of velocity with respect to time. So I'm always keen to point out that the units demonstrate a rate of change. Speed is measured in meters per second. In other words, how far something travels in a given period of time. Or in other words, the rate of change of displacement with respect to time. Now, many of those ideas will actually only come up, I'm sure, in AS mathematics, but it's nice to be aware of them because students will need to practice them in the future, and if they're doing kinematics at GCSE, then it's nice to be just a little bit ahead of them, recognizing how kinematics applies at AS and A2. I'd like to also emphasize right at the end that poor mathematical literacy is something that every one of us starts with. Nobody is born innately with excellent mathematical literacy. We are all poor at mathematical literacy when we begin. The only way we can improve it is with practice, and so it's vital that we all attempt these kinds of questions that might at first seem confusing or misleading. I am certain that after much effort, we all will understand the concepts that Newton himself developed after a great deal of hard work on his part. So thank you for listening. Bye bye.